Okay, let's quickly recall what we did last time. Well, only one slide. So we basically proved the halting problem, and then we proceeded to show that many different languages are undecidable by reducing them to a halting problem, specifically reducing them to K0, which was special halting problem. So this was strings of corresponding to all Turing machines that when you start them on empty tapes, they halt. So we'll see it in a moment, but what I want to remind you is the notion of reducibility, right? So I have two languages. So I fixed the alphabet. I have two languages, and one language, L, is reducible on L prime. So the idea is to somehow solving L prime, the problem of L prime solves L, but L is somehow an easier problem. You can think of it this way intuitively. But mathematical definition is L is reducible on L prime. If there's a translation that is a total computable function defined everywhere, this is total, and computable, meaning there's a Turing machine that computes it, such that for any string, a string is in language L if and only if when you transform this string, it is in L prime. So basically the question, if you're asking a question, is the string in my L? So you're trying to answer the problem L. It reformulated is you just apply F to your W and you reformulate it in L prime. And then there was an exercise which is very easy. We also talked about this last time, that if L is reducible on L prime, then if L prime, if you solve L prime, so you decide L prime, you decide L. And if you cannot decide L, you cannot decide L prime. So L is undecidable, L prime is undecidable. And then we saw this. And then there was some remarks about the equivalence relation on problems, so on languages. So two languages will be equivalent if they are, you can reduce one on the other and vice versa. But anyways, this was just a reminder. So now let's look again at different languages. So we have language C. So language C consists of all strings of zeros and ones, such that the machine corresponding to this string, so this is a program now, computes a constant function. This is C. K0 is the one I mentioned. This is all strings such that this string as a program started on empty tape halts. And C1 I just added here is all strings such that this string as a program, so this Turing machine MU, computes a constant function 1. Not just any constant function, but it computes a function whose value is 1 at every single point. And the idea is that none of them are decidable. And none of them are decidable. You can kind of intuitively think why this might be the case, because you are running, so you might brute force this and check whether your program computes constant function 1, but you can check it on only finite amount of natural numbers. You can never check on all of them. So you need some smarter way to tell that it always outputs 1. And it's somehow impossible to do it for every single program that computes 1 jointly. So we did this last time and we stopped here. And here the idea is that again we have the C1. These are all strings that MU computes a constant function 1. And how do I prove that this is undecidable? I reduce K0 on C1. So K0 I already proved directly is undecidable when I constructed this small argument, when I plugged back into, so you saw this argument last week, it's also in the recording. And so how do you prove that K0 is reducible on C1? And this will imply that C1 is undecidable. So I have to tell you function fu basically. So this function that transforms the input u. So instead of telling you and describing how this function acts, I can describe a Turing machine. And if I describe a Turing machine, then the Gödelization of the Turing machine, so this Turing machine as a binary string, will describe the value of f on u. So instead of describing the similar way as here, instead of describing what f does to input u, I will describe you for input u, I will describe a Turing machine, and the Gödelization of the Turing machine is the value of the function. So what does a machine do? So it takes, so for input x, what it does, it erases x. So it has x on the tape, it erases x, and now it also has input u. So the input is u, and so input is x, but somehow I'm constructing a machine for u. So what it does, it behaves exactly like mu, started with empty tape. So whatever mu does on an empty tape, the same thing does, this machine does the same thing. And if it halts, that means if mu halts on empty tape, it outputs 1. So now let's see what happens. What happens, I wrote it out here, is that let's say u is in k0. Remember, k0 is all those u's such that mu started with empty tape halts. So if u is in k0, that means mu started on empty tape halts. If mu started on empty tape halts, that means that this machine I constructed, f of u, started on x, outputs 1 for any x, because for any input, it just erases that input and then behaves like mu, and now I know mu halts, so then this outputs 1 for any x, right? And if it outputs 1 for any x, then it computes the function, constant function 1. So f of u, this guy, is in C1. So this is, so u is in k0, so this also goes back somehow. You can see that this goes this way. Also, by the way, I corrected some things here which is not uploaded to your teams, so this should be C1, not just C. But anyway, so you can start here and go back also, and in the end you end up that u is in k0 if and only if f of u is in C1. That means k0 is reducible on C1, meaning that C1 is undecidable. Okay, and you could, there's an exercise lemma 6 that C is undecidable is an exercise. So if, I mean, very easily you can reduce maybe C1 to C or something. Oh, this actually got an update. So it's basically always tricks like this that you do to do a reducible. I think in the previous exam last year there were a couple problems about proving that some things are undecidable. But okay, now watch what we did. If you go back here, so we proved that halting problem is undecidable. So you can never, there does not exist a meta program that takes in another program as an input and the input of another program as an input and tells you whether this program halts on that or not. This was halting problem. Then there does not exist a meta program that takes another program as an input that tells you, okay, this program computes a constant function. The same thing with C1 cases. So all of these things are undecidable. So now there is a Rice's, or I don't know how to pronounce this, Rice theorem, which is anything decidable basically. So do meta programs exist? You can think of it this way. And so the question is, can we decide any non-trivial property of programs, which is the same as Gödelization, mathematically speaking, of U? So can you have a meta program that takes inputs another program and decides something about that program? So maybe, does this compute a constant function? Does it halt on empty tape? Does it blah, blah, blah? And non-trivial property, I mean that there are some properties that are satisfied by all programs. So let's say all programs do something, then I don't count that because the answer is always yes then, or always no. So non-trivial property is a property that for some programs this property holds, and for some other programs it does not. For example, some programs compute constant functions, some programs do not. So can I write a meta program that decides whether another program computes a A constant function is a non-trivial valid question. And Rice's theorem states that such thing is not possible. So basically writing non-trivial metaprograms is not possible, and we should prove this, otherwise this is a famous theorem. So what exactly does it say? So most of the problems are undecidable, basically. It's worded this way. So let's mathematically precisely state it. So let's say I have set of all computable functions. So all functions that from 0, 1 and hashtag to 0, 1 and hashtag, so all possible strings of 0, 1s and hashtags to all possible strings of 0, 1s and hashtags, and all functions that are computable. Basically what I'm saying, this is a set of all Turing machines somehow that compute. So this is like a set of all programs. So they take an input and give you an output. This is what it means. And computable means that there is an algorithm that does this. So you can algorithmically take an input, do something, and give an output. But by algorithm, I mean, of course, Turing machine by Church thesis. And computable, this is exactly what it means. So let's say I have everything that is computable. This is R. And let's say this R is split in two parts, R1 and R2. So let me draw this. So it's like this. So this is everything that is computable. This is your R. And let's say I split it in two parts, R1 and R2. Meaning some computable functions go here and some computable functions go here. So input-output things go here, some go here. And so R is the union of R1 and R2. And this dot here, the small dot here, means that they have no intersections. There's no computable function which is in both of them. Somehow they're disjoint. So R1 and R2, and non-trivial means that they're not empty, meaning that if one of them is empty, then everything is R1 or everything is R2. I don't want that. That means that every computable function is in R1. I don't want this. So none of them are empty. So what I'm claiming is now that if I look at the set R prime here, which is all strings, that if I look at the string as a program, that is in R1. So these are all strings such that if I take a function that the string computes, the string is also a program. This is what MU stands for. It's a Turing machine with program. So string U, the Turing machine that string U defines, then this is a function that this program does something, right? So let's say I want to look at all strings as programs and the ones that are in R1, then that is undecidable. So completely generally, if I just take all programs that take inputs and outputs, split them in two and look at one, and I ask you a question, okay, give me a program that decides for any single one of other programs, is it in R1 or R2, it's undecidable. So completely generally, doesn't matter what R1 is. For example, we proved that if R1 computes a constant function 1, then it's undecidable. Or if R1 holds on empty tape, it's undecidable. But just in general, if you just split it in two, it's undecidable. So non-trivial things are undecidable. So metaprograms basically do not exist. This is what this theorem says. And how we are going to prove this is basically we will show that K0, which we proved directly that is undecidable, this special Horsling problem, can be reduced to this R prime. Whatever this R prime is, doesn't matter. You can reduce K0 on this by program transformation F. So what we will do is that we will construct f of u such that when you have a Turing machine M f of u will compute a function in R1, so here, if and only if mu started with empty tape holds. I will do this now. So I will construct this function f, let me repeat it again, such that if you start with string u, apply f to it, it gives you a program, and that program computes a function which is in R1 if and only if U as a program started with empty tape holds. So this would mean that U is in K0 if and only if f of U is in R prime. And that would prove that you can reduce, this is the definition of reducing K0 to R prime. So only thing I have to construct now is this middle thing here. Construct mf of U such that it computes a function in R1 if and only if mu started with empty tape holds. F mu to mf of U. Okay, so this is f of U. So I have to construct this and then I'm finished. So how do I construct this? By the way, it's actually very, if you really understand what is going on here, it's just generalizing this argument. So how does this generalization work? There exists, so by omega we denote a function which is everywhere undefined. That is a function that is not defined for anything. If you have dealt with Haskell, Lean, or something like this, those programming languages, you're familiar with this function. This is a function that is nowhere defined. So everywhere undefined. For every input, it loops. Basically, you can think of it this way. So call this function omega. It loops everywhere. And without loss of generality, I assume that this function is in here. So I assume the omega sits here. If it sits here, I will just rename R1 and R2, so it doesn't really matter. So I assume omega is in R2. And M prime is a Turing machine computing a function in R1. So I know that R1 is not empty. So it contains functions that are computable, right? So let's say it contains some function here, I don't know, some f, since it's not empty. So if the f is computable because the whole R was just computable functions, then there exists a Turing machine that computes M. And I take this Turing machine M prime. So since R1 is not empty, there exists a function in there, and that function is computed by some Turing machine, and just call it M prime. Because every computable function, by computable will mean computed by Turing machine. So M prime is a Turing machine computed by function in R1 because R1 is not empty. That's what it says here. And now I again define the new machine M f of U, right? So instead of defining what f does to U, so this is my goal to define the machine M f of U, right? And so that this thing holds is what does M f of U do? So I have to describe a Turing machine, I have to tell you what it does on an input. On input X, what it does, it just completely ignores this input, but saves this. So it has many, so let's say it's a one tape machine, so it saves it on extra track. So you know you can do this, right? You can ignore the input, but save it somehow. Maybe copy it somewhere, and then you have it. So ignore it, but save it. So you know what X is. Then again, behave exactly like mu started with empty tape. So it kind of emulates the previous proof. So it behave like mu started with empty tape. Now there are two possibilities, mu holds or does not hold. So that basically means is U is K0 or not in K0. So if mu holds, let's say mu holds, then I behave exactly like this machine M prime that I know exists. So I just picked one machine and whatever that is. I behave like M prime, but started with input X, which I saved. So this is the trick. And what is the function computed by this machine that I constructed? Now, if mu does not hold, that means U is not in K0, this function will be undefined. So this will be omega, so undefined thing. But if mu started with empty tape holds, I will behave exactly like M prime on X. So it will be the same function that M prime computes. So if U is in K0, the function is M prime. So I know now M prime is in R1 and I'm finished. So I got that U is in K0 if and only if f of U is in R prime, because M prime is in R prime. So basically I encourage you to look at it one more time. This actually finishes the proof, but it's basically emulating what we did here, but in more generality. Instead of C1, you take just anything. But it basically shows you that the meta programs do not exist. Let's pause the recording for a moment and just discuss this. So it was nice discussion. But now this ends the proof here, that basically none of the things are decided. So meta programs do not exist, as I said. This wording is also possible. But now we move on and push it even further and talk about universal Turing machines. But let's go back here and remind you what the universal Turing machine is. So let's look at the halting problem. So where is it? Oh, here it is. So let's look at the halting problem one more time. And let's try to understand it one more time really well. So what is a halting problem? The halting problem is pairs, so two strings. So hashtag is just a separator. So I have two strings, U and V, right? And so two strings, and only those strings are in H, such that U as a program, so meaning as a Turing machine, when I start this Turing machine on this input, it goes to an accepting state. So deciding halting problem would mean to have a meta program that when I give it an input U and V, will tell me, okay, U halts on V. That would be deciding H. But what would be accepting H? Accepting H is a different definition. It's not deciding a problem. Accepting H would say something like, okay, I know that U and V are in H. Give me a meta program that tells me that they're in H. So algorithmically gives me an answer yes, if and only if U and V are in H. And we talked about this last time. Can you recall what is this machine that does this? So I need a machine or a program or Turing machine, such as I give it input U and V, and it should tell me, okay, U halts on V if UV is in H. I mean, I'm premising it, so I'm not premising, so I'm putting an asterisk that if U and V is in H, but because you cannot do it otherwise. But can you come up with a brute force machine that does this? And you might have had an experience in real life with doing this kind of machine. So this machine is what it's supposed to do. Let me just tell you is that, so what it should do, let me write it. So this is H, right? So this machine is called the universal Turing machine. So I'll just call it U. So it should take an input U hashtag. So this is small u and big U. So let me write it differently. So this is big U, and it takes an input small u and V. And what it does, basically what it's supposed, it should emulate MU. So U is a program, right? So it somehow, this machine is able to decode the Gödelization and act like MU and run it on V. This is all it does. So this universal Turing machine is just emulates other Turing machines. It takes the other Turing machine as an input, the code of other Turing machine, and it emulates the other Turing machine. So now this machine halts. What does it mean? If this machine halts, that means U hashtag V is in H, right? Because if MU on V halts, U hashtag V is in H. And if U hashtag V is in H, then this machine will halt. However, look, if U hashtag V is not in H, then what the big U will do is it will emulate MU on V and it will never halt. So it can never give you the negative answer somehow. That is the universal Turing machine. Okay, anyways, so let's just go back here. Where is it? Oh, here. The universal Turing machine So again, there you see the caveat here. We already talked about this, but there exists a universal Turing machine U such that for all U and V, machine U started with U hashtag V simulates MU started with V. And there is a very quick proof, I guess. In C, you can write an interpreter. That's what they called U prime, which with input, I think you've done it maybe, I don't know. With input U hashtag V, decodes U to a Turing machine. So U is a Gödelization, right? You decode it to a Turing machine, then act as this Turing machine on V, and then you just simulate it by one tape Turing machine. And this such thing exists. You can actually write it down. As I said, I think with 4 states it's done. You can Google it and you'll see different ways to create a universal Turing machine, and it's doable. You just write it down and it does this. And the observation is that this is, as we discussed now, it's an acceptor for the halting problem. So the halting problem has an acceptor. It is undecidable. We also proved this. However, it's acceptable. And now I have this question here, and I want you to answer. The lemma here says that the language is decidable if and only if the language is acceptable, the language has an acceptor, and the complement of this language also has an acceptor. Can anybody say why would this be the case? Let me pause this before you think. So the idea you said is correct, but it goes both ways, by the way. So the one way is if you have the 0-1 answer for L, then of course you have acceptors for L and L bar. This is trivial, I'll leave it up to you. And the other direction is dovetailing, exactly what you said. So if you have an input W, you just alternate between simulating one step of acceptor for L, and so let's say acceptor of L is A1, the program is A1, and acceptor for L bar is A2. Then what you do is you make one step on A1, then one step on A2, the second step on A1, second step on A2, and you do it until one of them succeeds. And you are guaranteed that either A1 or A2 will stop because your W is either in L or L bar. So one of them will succeed, and then you can, if A1 holds first, you output 1. If A2 holds first, you output 0. Okay? So basically, decidable means that the language is decidable means that the language itself and the opposite language has acceptors. This has a very weird implication now. The implication is that H bar, the opposite of the halting problem, does not even have an acceptor. Because I know that H has an acceptor, even though H is not this undecidable, H has an acceptor, namely the universal Turing machine is an acceptor for H. If H bar would have an acceptor, then H would be decidable, because you could do this dovetailing. So H bar has no acceptor. Not only is it undecidable, it's unacceptable somehow, H bar. And to describe it in words, what is H bar? H bar is all those strings such that the first string as a program started on the second string does not halt. Because it halts, but the fact that it does not halt, it even complicates other things. So basically, H bar has no acceptor. And now we move to a very important topic. This is the continuation of this topic, is the recursively enumerable languages. And recursively enumerable languages is another way, a mathematical way, or another way to describe the languages that have an acceptor. And let's first give you a definition of what it means to have. This was defined first, and only then I think Turing and Church came up with accepted and decidable languages. But recursively enumerable is a language, L, if there exists a Turing machine such that when you start this Turing machine with empty tape, it outputs exactly the words of L in some order. So let me explain this even further. So the language will be recursively enumerable if, when you start your Turing, there exists a Turing machine which you start, let's say, on empty tape, and it outputs one string, then outputs another string, another string, another string, and these strings are just exhaust all L in some order. L is countable, so we always know it's a subset of a countable thing. So actually we're treading deep waters here if you think about it. So L is countable, so a recursively enumerable basically means that there is an algorithmic way to list all the elements of L. It might be that it's not even recursively enumerable. That means there is no algorithmic way to just even indicate what the elements of L are. H bar would be that, for example. But anyways, this is recursively. Is it clear? So it basically you start, there must be a program that when you start, it goes on infinitely, but it outputs at some point, every single string of L will be outputted. Maybe after quintillion years, but it will happen. Right? This is what recursively enumerable means. And it turns out recursively enumerable and has an acceptor is the same thing. And here is the lemma. L is recursively enumerable if and only if it has an acceptor. So I will show you one direction and the other, well, maybe... Okay, maybe you can tell me both of them. Let me pause this and let's still discuss again. Okay, so the discussion is very fruitful. So again, first we record the first, so what you said. So I assume that there is a machine that enumerates my language. So how do I construct an acceptor? M prime for L is, for each input W, I just list I run M on empty tape and I enumerate all strings V1, V2, V3, and if W is in L, at some point Vi will be equal to W. And if true, I stop. If it's not true, I will never stop. I will always be waiting, comparing and waiting, but acceptor only requires for me to stop only when the string is in the language. So that's fine. So now, the much trickier option is going back, and I don't think you can think of it, but at least let's try. Let's say I have a machine that is an acceptor. That means I have a machine such that any string I give it, it says, okay, this string is in the language if the string is in the language, if and only if the string is in the language. Otherwise, it might loop. How can I produce all strings of this language? So I want to go back now. I want to list all possible strings now. All right, so as you said, so basically the idea is correct. So you make, so let's read it. So the slightly trickier part is you have an acceptor for L, and exactly as you said, but this just describes the implementation of that as well, of your idea. The idea is that tapes are infinite, configurations are finite, so you can do what you said you would. So you introduce every single new letter on every step and make a consecutive step for every one of those. So basically, first, as you said, you enumerate all possible strings. So you enumerate a star. So if it's zeros and ones, you enumerate zeros and ones and hashtags or whatever. So you enumerate everything by length, maybe, whatever, or by equal length and lexicographic order. And now we proceed in rounds. In round one, we create a start. So basically the way you implement what you said is you write down configurations of your Turing machine. So making one step there and making two steps there is basically you write down the complete configuration with a finite string and then just move your head. So in round one, you create a start configuration K1 of M started with V1. This is what you said. You start with V1 is you just write down the configuration. And in round two, let's say, you simulate one step of M for each. So in round 2, you would simulate one step for configuration of the previous word, and each such step might require, by the way, so basically you write down the configuration, then make one step, write down another configuration, make one step here, 2 steps here. Right now the third configuration on the one tape, and you make one step here, one step here, one step there. And basically it might happen that the head that you're recording, where it is on the first word, let's say, shifts over to the second word, so you have to shift the whole tape, but that's not a problem. So this might require to shift the tape encryption of the configuration to the right or to the left, and if step Ki leads to an accepted configuration, you output Vi. So exactly as you described, this is what I'm doing, but how I implement them is I write down the configurations. So the configuration started on the first word, configuration started on the second word, the third word, and so you simulate. So on the first step, you make one step on the first word. On the second step, you make one step on the second word, also one step on the first word, meaning it's the second step on the first word. In the third round, you introduce a third word, make one step on the third word, the next step on the second word, and yet again next step on the first word. So this is exactly, but how you do it is you just write down configurations. So as I said, you do this, and on the tape as a new, so every time you introduce a new word, KR of the configuration. So basically this would guarantee, as we discussed already, that you will output the required words in some order. So every word that is in your language will be outputted at some point. However, those words that are not in language, that might loop, your machine will just continue working on them, but it doesn't really matter. All the words will be outputted, so your language will be recursively enumerable. So basically what we proved right now is that has an acceptor and is recursively enumerable is exactly the same thing. So you might have defined these languages as recursively enumerable. So for example, we just proved that H bar is not recursively enumerable because H bar has no acceptor. If H bar had an acceptor, then H has an acceptor. We know the universal Turing machine, so that H would be decidable. It's not possible. So we just proved that H bar is not recursively enumerable. So there exists a countable language that is not recursively enumerable. But now what we prove is we conclude the Chomsky hierarchy. So the last step in Chomsky hierarchy is that let L be a type 0 language, then it has an acceptor. So basically I go here, I copy it here to remind you about Chomsky hierarchy of grammars. So type 0 had no restrictions. Type 1 was context-sensitive grammar. Type 2 was context-free grammar. Type 3 was regular grammar. So for this we had, let's say we had DFA for this, which is, by the way, the same as NFA. For this we had push-down automata, non-deterministic one, non-deterministic push-down automata, and we skip this. We will talk about this also. This will be special kind of Turing machines, but in general these are Turing machines, but type 0. But what does it mean that the language is accepted by a Turing machine? This means that it has an acceptor. Doesn't mean it's decidable. So this is exactly what we're proving now, that if language is type 0, so it's created by a grammar which has no restrictions, then it has an acceptor, which is the same as there exists a Turing machine that just outputs the strings of this language in some order. So you can think of it how this might be useful, meaning that, okay, let's prove this and then we discuss if we. So let's say my language is type 0, so that means it's generated by some grammar. So how would I construct an acceptor, right? How would I know if W is in my language or not. So the acceptor means that if W is in my language, my machine must halt. So on input W, what I will do, I will enumerate all derivations of G, because now it has finite amount of productions, so I can enumerate all derivations because there's a finite amount of productions. So I can just, as the same exact way, if I have finite amount of letters, I can enumerate all of them by length and then lexicographic order. I can do same exact thing with derivations, right? First I start the shortest derivation, I enumerate all of them, then one longer derivation, one longer derivation. So I will enumerate all derivations, and if any such derivation produces W, I will accept. So I start with W, I save it maybe on a tape, and then I look at all possible derivations and I compare each one of them. And if I find W, I say yes. But if my W is not in my language, this might never stop, of course. That's why it has an acceptor. So basically writing down derivations and production rules is basically the same thing as creating an acceptor Turing machine. So this is a hand-wavy proof, but you get the idea. And now the other way around. The other way around, if I have a language, which is, by the way, I ban B from this language because I want to use B for my Turing machine. So let's say my language is, again, some language A star, but doesn't contain symbols B. If it does, I will rename those symbols something else. It doesn't really matter. So let's say it doesn't contain some symbols B because I want to use it for my Turing machine. And let's say this language has an acceptor. So I'm going back now. So here I proved if it's type 0, it has an acceptor. Now I want to prove that if it has an acceptor, it's type 0. That means I'm supposed to construct a grammar from a Turing machine. So I have a Turing machine that for any string tells me yes if the string is in the language, and it only tells me yes if the string is in the language. Now I want to construct a grammar. And the idea of constructing a grammar is so on a string W, I will save the string somehow. I will always save it somewhere. And then I will do all possible productions downstairs. So you'll see, so I have to construct a Turing machine, right? Oh, again, I have to construct a grammar. So given an acceptor like this, I will construct a grammar such that this grammar exactly generates the words that are accepted by my Turing machine. So what I said, I should have said it the other way around. So I construct a grammar, right? So I save the word in my grammar somehow, and then I run my Turing machine. So imagine I have like 2 tracks in my grammar. I will show you how I do it in a minute. But let's say I have 2 lines on my grammar. On upper line, on upper track, I save the word, and on lower track, I run my Turing machine. And if my Turing machine accepts, I have to derive the word that I saved. That's basically what I'm going to do. For this, what would be my non-terminals will be all the letters and also pairs of letters, states, and some auxiliary letters A1 and A2. And basically, these are to keep track. So let's say, so this will look like, so my non-terminals will look like this. So it will be like 1, let's say 0, and then now I might have 2 tracks, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, like this. And I might have a state here, Z1, and then, of course, maybe 0 like this. And then I will also have S, and I will have A1 and A2. I will use them. You'll see in a minute how. But basically, the idea is that, so it's letters, my non-terminal, pairs of letters. So I wrote them this way, up and down, so it's an upper track. Here I will always just save the input, and I will operate my Turing machine as if this was a configuration operating on this input here. And if I end up with outputting the upstairs, I have to accept. This is what I'm going to do. And so exactly as I explained, the intuition is that these pairs occupy 2 tracks, A1 on upper track and A2 on the lower track. And This is the same thing. Intuition for the next rules. So for possible inputs, a Turing machine M, the grammar can generate strings of the form like this. So for every input, so every input you give me, so let's say if you give me input 0, 1, 1, 0, I should be able to generate, my grammar should be able to generate something like this. Z0, 0, 1, 1, 0, 0, 1, 1, 0, and then blank, 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 whatever, however many blanks I need, and then blank, 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 like this. And what then, if I am able to generate this in my grammar for every input, what I'm going to do, I'm going to run my Turing machine. Come on. So I'm going to run my Turing machine here, basically. So it will be like your start state running on this input, and I will not touch this. And if in the end, when this goes to an accepting state, this thing is written here, then I will accept. This is basically what I'm doing. There is nothing fancy. And in order, but first of all, what I have to do is I have to be able to generate this kind of thing for any input. For this is the productions I need. From S, I can generate BBS. So think of the first B as upstairs and the second B as downstairs. So S generates BBS. So basically, let me just write S generates BBS like this. And it also generates Z0A1. So imagine Z0A1. So what is A1? Now A1 generates AA. So I want to generate this kind of things here. A on upstairs, A downstairs, A1. And it generates A2 for all letters. And now A2 is the rightmost part now. A2 is to generate these things here. It generates BBA2 and it disappears. So basically this, if you stare at this for a moment, it's trivial to see that this thing just generates this kind of thing for any W. Any W I give you, you start with the start state, you generate as many blanks as you want. Then from start state, you generate the start, from start state S, you generate the start state Z0 of the Turing machine, like this Z0 here, A1, then A1 will generate any string you want like this, and then A2 will generate blanks and disappear. So something like this will be generated. This part from S, this part is from S2, this part from A1, and this part from A2, just roughly speaking. So something like this will be generated, and next thing you want to do is you want to start running your Turing machine downstairs. And this is what this thing is doing. So simulate M on the lower track and remember the input on the upper track. So what does this mean? So if I have something like this, let's just look at the first one. And so the first one says something like this: CB ZDA. This one generates Z prime CBDC. And you have this production if and only if in Z when you're reading A. So when Z is reading A, you go to Z prime, overwrite C and go left. So what I did is here I overwrote this with C and went left, and I didn't touch the upper stairs. So basically, I'm operating the same exact way as the Turing machine operates here. And this just means that I went to Z prime, overwrote C, and went left. And the same exact thing you do by going to Z prime, neutral, and going right. So basically, what this derivation rules in your grammars ensure is that your machine can now somehow, you're simulating your Turing machine in your grammar downstairs. And then if it reaches the end state, so if you ever see an end state here, let's say you see ZE, something like this, the end state, what you're supposed to do is you throw away right components of pairs, meaning the downstairs, you ignore the downstairs. And for all Z, so how you do this is you introduce this here. What this does is, so basically, let me write this again, just so if you had AD, from here you can get ZAZ. So you just ignored D and doubled Z. I think you might as well avoid doubling Z, but whatever. So if Z is on the other side, you can do the same. So you're basically ignoring D if you went to the accepting state. This is the crucial, that this is an accepting state. And finally, you also throw away the blanks. So you have a derivation that you can always throw away blanks. And if your Z is an end state, you can throw away Z. So this will throw away these things also. And in the end, the only string that is derivable will only happen so that if your Turing machine that is emulated on the lower track goes to an end state, then you will be able to throw away all the things, and whatever you ended up with upstairs will be somehow derived in your grammar. So your grammar will only derive the words that are accepted by your Turing machine. It's just an overcomplicated way of simulating the delta functions by production rules. This is all it's saying. So every delta function is simulated by a production rule, but meanwhile, you also have to remember the initial input. This is the only thing happening. And the grammar can also remember inputs the same exact way the Turing machine remembers it on a separate track or or a tape. The same exact way grammar can remember it by just considering tuples instead of just one symbol. So actually, let's record it. This rules 1, 2, 3 ensure that any string, any possible string, can be written like this. Where is this I wrote? Come on. Here, any string, not only 0, 1, 1, 0, but any string can be brought to this situation. This is what 1, 2, 3 ensure. And only then you start operating on the lower string. And if your lower string goes into an accepting state, lower track goes into an accepting state, then you're able to throw away your B's, your Z's, and everything, and the upper track will be left as a derived one. Otherwise, what you want to derive is non-terminals, right? Your non-terminals are, where are my non-terminals? Here is, the non-terminals are only the alphabet symbols minus B. So if there's something left with B's or with Z's like this, this will be not a terminal thing that is derived. The only terminal string or string of terminals you can get can only happen if your Z0 at some point went to an accepting state and erased the lower part. And then, yeah, and so this actually proves that type 0 languages have an acceptor. This actually proves that the type 0 languages are exactly the recursively enumerable languages, because we proved that recursively enumerable and type 0 exist. And now we also proved that there are undecidable type 0 languages. And why is an easy question, and you can answer because you just have to connect all the dots, because type 0 is, for example, halting problem, right? Halting problem has an acceptor. That means it's a type 0 and it's undecidable. So some of the type 0 languages are undecidable. However, we just proved that there exists a language which is not even type 0. Can you tell me what language is that? It continues. The language which is not even type 0 is the H-bar. So halting, it's the, what's the name? It's escaping me. Come on, blank. Oh, yeah, the complement of the halting problem is the type 0 language. Well, it's not even a type 0 language because it doesn't have an acceptor. So there, even in our Chomsky hierarchy that is concluded now, type 0 means accepted by Turing. It's not concluded, by the way. It's this one we have to stay. I will specify these are linearly bounded Turing machines and blah, 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 are context sensitive languages, but we will do this. But so there's type 0 something, something, something. And type 0 is the most general type of language that can be specified by an algorithm. It can be specified by a Turing machine that just will list you all the strings of this language. But there are languages that are completely not specifiable algorithmically. That means they're not even conceivable by human mind somehow, theoretically. But that's besides the point. The next topic that is coming here is the recursion theorem by Kleene, which I actually skipped during the last semester. But I'm not going to skip it now, because why not? This is a very interesting question, and it hinges on this theorem called, it's basically a version of a fixed point theorem. I don't know if you heard this in functional analysis or maybe even in linear algebra. The fixed point theorem is usually something that is described, how do you describe it? So you have a function that maps something to something, and there is one point such that this one point is mapped to itself, basically. This is a very general statement of the fixed point theorem. You know the fixed point theorem about the maps, right? Let me give you a very high schooler's description. So what I'm claiming, and maybe you can think about it, so this is a Brouwer's fixed point theorem, for example, for your demonstration. If I have a map of Kutaisi in my hand, and if I put it on the ground, this map of Kutaisi, if I put it on the ground, now every point of the map, on the map, corresponds to a point in Kutaisi, right? You agree, right? If you look at the map, there's, let's say, Gelati there, or maybe Bhagrati Church, and then there is a point on the map that corresponds to Bhagrati Church. What I'm claiming that at least one point on the map sits exactly on top of itself on the ground. This is a weird statement that we explained this in Georgian. Okay, I tried to explain Brouwer's fixed point theorem, but if you had not, so you will, some of you will continue doing this. Fixed point theorems are all over mathematics, and this is one of them here. And let's just explain this. So what is the question? The question starts maybe like this. Does there exist a program or a Turing machine such that this program started on empty tape prints its own Gödelization? Meaning, can you think of a program that prints itself? If I ask you this now, some of you are really good at coding, can you write the code that exactly just prints itself as an output? Think about it for a moment. Can you do this? Okay, so such a thing does exist, and this is the recursion theorem by Kleene from 1938, and it's very interesting, and it hinges on a fixed point theorem that I discussed. So the notation that I'm introducing is even more, so try to prepare your brains. So if u is a string, by phi u I denote a function that your u is a string, right? It's also a Turing machine, meaning a program. That means it's also a function. So by fu, phi u, I denote the function that machine u computes. So your string is also a program. That means it computes some inputs and outputs. So it's a function. So that function, by that phi u, I denote is the notation for that function. So it's the function computed by Turing machine name of u. Okay. And here is the fixed point theorem. What I'm claiming is that, let's say h be any total computable function, meaning it sends strings to strings and it's computable, meaning there exists an algorithm that computes h, so it's basically a program. Better way to think of it is a program transformation. It's a program that operates on programs. So it takes in strings and outputs strings, but the strings should be thought of as programs. So it's a program transformation. Then there exists a string u such that if I take the string u, treat it as a program, and look at the function that it's computing, it computes the same exact function that if I take u, apply the transformation h, look at it as a program, and then look at it as a function. So basically what it says that psi of u, there exists one point u, such that psi of u is equal to psi of h of u. So u is a fixed point of h as a program. This is what it says. So it's a fixed point theorem. So i.e., the original program u and the transformed program h of u compute the same function. Such programs always exist for any transformation. So I'm theoretically basically proving this, that I asked you to do, and this is a mind bend. So the proof is like magic. You can see that there's magic happening here. What I'm going to do is I'm going to construct a total computable program transformation g tilde. How? Such that psi of g tilde x, so what is psi of g tilde x? Let me just, g tilde u of x. So I start with a string u. I apply g tilde. I will say it in a moment what g tilde is. So I will apply g tilde. I will look at the program that corresponds to u applied g tilde. That program is, of course, a function that takes inputs and outputs, and I will give it an input x. And this would be the same as taking u, looking at psi u of u again. So what this means, I'm taking u, giving it to m of u as an input, and computing f there and giving it x as an input. So this happens when psi of u is defined. Okay, I know if it's the first time you see it, it's very hard to follow all the twists that is happening here, but let's just construct g tilde of u, and then maybe you can then look at the recording when you go back and look at it. So how I have to construct g tilde of u that this satisfies this. So what is the program for computation of g tilde of u? I will, instead of constructing again as I did before many times already, instead of giving you description of g tilde of u, I will create a program for computing g tilde of u. So first what I do, I decode the transition function mu from u. So it takes an input u. So I have u here, right? That means I have m of u. That means I follow the Gödelization and so on and so forth. I look at the Gödelization and I look at all the delta functions that are written there, right? So I know that the transitions of m of u. So now I create code m of the following machine. So now I know m of u, but I'm creating now Gödelization of a different machine. What machine? The machine I'm creating Gödelization for is I save input x on some track, then I run mu with input u, so x is saved somewhere, so I run mu with input u. If this holds, that means if u is in k0, if this holds and the result is some string e, I run the universal Turing machine with input ex. That means I'm simulating me on x. So I'm basically doing this here. If this terminates, I output the result of the simulation. So I basically described this. So I started with input x, I saved it somewhere, then I simulated mu on u. If mu on u halted with some output, I simulated that output as a program on x now. So I did psi of u on x. So I basically did this, but if mu on u does not halt, it's undefined. So basically I gave you a Turing machine descriptions of G tilde of U. That means G tilde of U is always defined. So it's total, so it's defined for every U. Even though psi G tilde of U might be undefined, G tilde of U is just is exactly this. Computation is written out here, so it's all total because M G tilde of U is defined as follows here. Okay, your brain is probably already gave up, but anyways, let's push it even further. And this actually concludes the proof. Why? Because G tilde is now total. H is computable total. That means if I take first G tilde and then take H, it's computable by some Turing machine. If it's computable by some Turing machine, let's call that machine MV. So this means that psi of V is Fm of V. So G composed with H is computable by some Turing machine V. MV basically. So Turing machine recordalization V. So this equals this. Then psi G tilde of V, by the definition of G tilde here, is psi V of V, like this, which is psi V of V. So it's the first line of the definition, and this is defined, so it's like this. So psi V of V is by definition H composed with G psi of V. So this is all is written here. And in the end, I take U equals G tilde of V. So if you plug in here U, you will get psi H of U is equal psi of U. So this theoretically proves that such program must exist. Well, it doesn't prove anything yet. I have to do one more step, but this proves that such for every program transformation, the fixed point exists. Huh? So it's not equal. G tilde V is something, right? Let's call it U. So let's call G tilde V U. Then here you have psi of U, right? V is a concrete string. What string is V? V is a concrete string that computes this composition is computable. That means there exists a Turing machine that computes it, and V is the Gödelization of that Turing machine. So V is fixed. If V is fixed, I can compute G tilde of V. And whatever G tilde of V is, that is, I just call it U. And here I just write U, and here then it comes out that psi of U equals psi H of U. Using the definition and the definition. So two definitions, this one and this one. So U is, I just plugged in, U is just a name for G tilde V. But that means that this such thing exists. And let me melt your brain even further and conclude the whatever. And then I will stop and we ask questions if we have them. I'm not going to go to proof systems. Oh, tomorrow I can go to proof systems, right? We have one lecture tomorrow, right? Okay. Okay, let's finish this lemma then. Let's go all the way. There is a Turing machine MU such that MU started with empty tape prints U. So the initial question. So I proved this now. So I proved that for every program transformation, psi H of U, there exists U such that it has a fixed point, right? So now I consider the program transformation, the specific program transformation H, for which I know that such thing will exist. So what is the program transformation H? I did a lot of edits here, by the way. There were many mistakes. But I have not uploaded this, but it will be in the recording. So what does this program transformation H do? So again, I'm describing M H of U. Instead of describing what H of U does, I'm describing what the Turing machine corresponding to Gödelization of H of U does. So with input X, what does M H of U do? It prints the Gödelization of the machine DU. What is machine DU? DU is a machine that when you start it on the empty tape, it just prints U. So when you start it on empty tape, it prints U, and if you do not start it on empty tape, it does whatever you want. I don't care. But it's not the same thing as M of U. M of U is what? Let me remind you. M of U is the machine which has code U. M of U is a machine that when you look at it as a string, it's U. But D of U is a machine which on empty tape prints U. It's a different thing. And on input X, it prints the Gödelization of D of U. So by lemma 15 now, if I start psi U on epsilon, then there exists such U, right? I know. So this is the same as psi H of U on epsilon. So, but now what does H of U do? It runs the machine MH of U with epsilon, which basically what it does, it runs du. So, yeah, by the way, I forgot to say that after you run du, so you print the Gödelization of du, which is a machine started with tape U. Du is a machine that started on an empty tape, it prints U, and then you output when you run du on X. So if X is empty, you will output U. This is precisely what it says. If you take empty here, you will output whatever du outputs on empty, which is the result of du started with empty tape, which is U. So this program transformation, psi U on empty will output U. So exactly we will write that psi H U is equal psi of U on empty, and on other things also you can check that it works. And this is the mind bend of the Kleene's recursion theorem. But should I clarify why this works on other things than empty? No, you think about it. So I will advise you to go back, look at it if you want to really look at it. I will try to squeeze something on this in the exam. But I might not succeed. I'm warning you to find an exercise on this. But it's a very nice theoretical computer exercise done by Kleene. Okay, let's stop. And if you have questions, we ask questions, the general ones. And if not, we continue tomorrow with proof systems.